Yeah. So as I was saying, right, I don't think we went over how to graph these on our graphing calculators, right? So reviewing real quick from Friday, or maybe not so real quick, right? We talked about polar coordinates, right? Which fundamentally changes how we graph things, and with that fundamental change, that very kind of basic, at the most basic level kind of change, it really affects kind of like our, typical or our paradigm that we had for graphing things, right? Typically, right, when we graph things, we worry about going left, right, up or down kind of thing. But in the case of polar coordinates, you're still going to use two numbers to locate a point, but instead of using left, right, up, and down, you're going to rotate an angle theta from your polar axis, which is like the positive part of the x-axis there. You're going to rotate an angle theta, okay, about this thing, the origin, but we're going to call that the pole now too. Rotate that angle theta, and then extend r units in the direction of that angle, or if it's a negative r, you're going to extend r units in the opposite direction of that angle, right? And so this gets, we get a little disoriented now, right? Typically, right, when we graph a point, we normally use the first coordinate, and then we graph the second or use the second coordinate, and then to find the point. But in this case, right, we normally start with our angle, and then we use our r to, kind of extend out in the right direction, right? And so we had all these different, coordinates here. We came across the fact that, for example, here, two different coordinates, right, b and I, their coordinates are not at all the same, right? One is positive 4, 5 pi over 6. One is negative 4, 11 pi over 6. And they both identify the same point, same location, I should say, all right? Which is unlike what we talked about in rectangular coordinates, right? A single rectangular coordinate describes a single point, right? Every coordinate uniquely describes a point in rectangular coordinates. But here in polar coordinates, every coordinate every location, right, can be described by an infinite number of points, right? There's two coordinates here that describe this point, but really there's an infinite number of possible coordinates you come up with for this point. So that makes things a little bit weird. All right. We talked about converting from rectangular to polar and then vice versa, right? We had some relationships here that we want to be familiar with, right? We want to remember here x squared plus y squared equals r squared, right? If r is like the extension, of that polar coordinate there and the angle theta, that creates a right triangle here if we use x and y as legs. And so we have the Pythagorean theorem, right? Also within that, we have the trig relationships here. The x coordinate is merely r times the cosine of the angle theta. Y is merely r times the sine of theta, which makes finding the x and the y coordinates pretty easy, right? And then tangent of theta is y over x. We converted some polar to rectangular, which was, pretty straightforward and easy. And then Mr. Whitmire had some troubles right here, right? But then what the issue was essentially is that I was trying to find the things in the wrong order, okay? You want to find your theta first and then find your r. The reason for that is because the theta is what kind of creates the multiple angles. I guess technically there are multiple points, multiple coordinates you can come up with. So r, I guess there's two varieties, but anyway, it's the theta you want to nail down first. So solve for that theta first. I mistakenly solve for r first and then use that to solve for theta. So go in the other direction. Here is what I did that. I solved for the theta and then found those theta values and then used those to get the x and y coordinates and stuff like that. Okay? So, use the theta value and then and the x and y's to solve for the r's. Okay, and there were like two different polar coordinates that describe that single rectangular coordinate there. All right, so again, find theta first, then find r in those situations. And then we graphed, right? Then we graphed some things. Some things weren't too terrible, right? Like r equals 2, for example. That was pretty easy. Just when we made our table, right, r was always 2 no matter what angle theta we made, and so that created that circle centered at the origin or the pole with radius 2, which again, r equals 2. It's like, duh. Okay? And we converted that into rectangular using that relationship that we had from before where x squared plus y squared was r squared. If r was 2, we just plugged the 2 in for r. Okay? Here we also then kept theta constant. What happens when we keep theta constant? Well, we created a line. Okay? That means our r's would change, and so it just creates this line here. Again, we could use the relationship tangent of theta equals y over x, and we plug then the pi over 3 in for the theta, because again, our original polar equation was this, so we could just replace theta with pi over 3, and then solve for y in terms of x, like that. And then finally, r equals 2 cosecant of theta. That was an interesting scenario, okay, which also I think showed up in our homework, or we had like a secant maybe or something. Anyway, I think we had something like that in the homework too. So we saw that, and that actually created a horizontal line. Pretty crazy stuff. Okay. And then we went to the snail. Okay. Right there. and again, graph different things, and it's helpful, right? So just to kind of refresh our memory a little bit about the graphing of these things, right? So we started with the theta 0 and at r value 2, so 0, 2 right there. And then we knew that the very next point, or so we did then pi over 6 just for like ease of calculation to help us. We chose pi over 6, and we skipped like pi over 4, we skipped pi over 3, because sine of pi over 6 is a nice number, right? Sine of pi over 6 is 1/2. It's easy to do the math with that. We skipped pi over 4 and pi over 3 because those would have given square roots, and it's harder to, kind of like quickly calculate those. But pi over 6 is easy. It gave us 0. And so here's like, this is a very important, concept we need to make sure we have down, right? We knew that we had to go from the point 0, or I guess I should really say 2, 0, right? The point 2, 0, which is r2 and theta 0, to the point -2 pi over 2, right? And this is, or sorry, it's point 0 pi over 6. Let me not get ahead of myself here, okay? And this is where it's crucial, right? We can plot that first point, no problem. There's our angle 0. It's just on the polar axis. We go 2 towards it. But then we know that we have to go to this point, pi over, or 0 pi over 6. So at the angle pi over 6, we're at the pole, okay? But again, by kind of this idea of the intermediate value theorem, right? This is a continuous polar equation, polar relationship here. We have to go from our r values of 2 down to 0. So as our r value shrinks from 2 to 0, that means we need to get closer and closer and closer and closer and closer to the pole, right? And that's while we are rotating from 0 through pi over 6. So while we kind of like rotate through from 0, the angle 0 here, through to pi over 6, we have to make sure we get down to 0 by that point. And that helps us to kind of like connect those things in the way we in a way that's atypical from rectangular, right? Rectangular, we kind of like to a straight line kind of thing, but this, it's, we have to curve it to get around to the point there. And then likewise again, from the 0 pi over 6, we have to go to -2 pi over 2. So that means we have to go from 0 to negative numbers. And so, from our pi over 6 angle right here, pi over 2 is right here, okay? But pi over 6 to pi over 2, we're going to rotate through these, right? But you're like, ooh, but it's negative numbers. And so instead of being through this section, we have to flip it through and down to here, okay? Because it reflects, right? Instead of going towards those angles, right, from pi over 6 to pi over 2, towards those angles, we instead have to go away from them because it's a negative. All those radiuses are going to be negative to go from 0 to -2. Okay? So that is like a fundamental idea about how we want to be able to sketch these, right? That's going to help us kind of quickly sketch. And that is a bit of a change, right, from our rectangular stuff. So we want to be familiar with that. But also, right, don't forget we also have our graphing calculators available to us to help us out with this. So, for example, I want to show you the rows here, but we won't use, we won't like do the table. I just want to show you on the graphing calculator. And you can kind of get, again, more of a appreciation for how we're graphing these things, right? You'll see instead of graphing from left to right, like our graphing calculator normally does, it's going to graph rotating around the pole. So, in your graphing calculators, make sure the mode is set to polar. Okay, and then we're going to graph 4 cosine 3 theta. Okay, you just type that in your calculator. Make sure your mode's also in radians. It is here, and I'll graph that. Oops. Okay, and so there is our. Let me see if I can make that a little bit nicer looking. Okay, let's try that. Okay, there it is. Okay, and there's our rows. And so if I can, I don't know if I can, I don't think I can slow it down here, but let me try like 1. Try that. That's too slow. Okay. Okay, so there you get it. I'll slow it down a little bit. So there you can see we're rotating around the pole here. Okay, so see, it's not left to right, it's a rotation around the pole and stuff like that. Okay, you guys did anyone in here ever play with a spirograph? Yeah, it's like an ancient toy from like, way back when. Yeah. So no, that's an Etch-a-Sketch. The spirograph is like it's like a circular thing, but it's got gears. Yes, exactly right. And so I mean, it's like that was actually like polar graphing in a sense. That was used, it kind of like has a relationship to that, kind of thing. So anyway, yeah. My window, I made it from -5. So right. Let me talk about that. Right. Just like we have parametric, right? We have a kind of parameter when it comes to polar too. It's like theta, and so your theta min, your theta max, you can like have it do more than just from 0 to 2 pi here. You can have it start from negative 2 pi to 2 pi, whatever you want kind of thing. Because of course we can have an infinite, kind of range there for our pi's. Also the step, that's how I kind of slowed down my graph, is I made my calculator, like I think normally the step is, I don't know, like maybe pi over 12 or something like that. But if you make it like do, a smaller step, it has to calculate longer, so that's why it slowed it down kind of thing. And then of course here's how you adjust your x min, your x max, and your y min and y max, which is your left, right, and your up and down. So that helps you see that. All right. But there it is. Alrighty. So we're not going to do that though right here. We're going to continue on though to polar coordinates and calculus. All right. So now let's put these two things together. Yes. With calculus. Okay. The good news is this is very similar in scope to our parametric stuff that we've been doing. All right. So don't forget that parametric stuff, right? We have all those relationships, especially like the position, velocity, acceleration things, and the arc length and stuff like that, right? Don't forget that, right? Because we haven't. This kind of relates, but it's not, exactly the same as it. So you want to make sure you're holding on to that while we also get into this. Okay. So anyway. So polar coordinates calculus, if f is a differentiable function of theta, then the slope of the tangent line to the graph of r equals f of theta at the point r comma theta is found the same way as a parametric equation. Okay? In fact, we will convert polar equations to parametric equations using the relationships. Okay? So if you remember from parametric equations, the first derivative, right, dy dx in a parametric was y prime of t over x prime of t, or dy dt over dx dt. Well, in terms of our polar stuff, it's going to be dy d theta over dx d theta. Right? And that's all there is to it. So we'll have to find an equation for y, and so in other words, to find the derivative of y with respect to x, we will find an equation for y in terms of theta and take its derivative with respect to theta. We'll also then find an equation for x in terms of theta and then take its derivative with respect to theta. Okay? So that's what we're going to do. And then put those, of course, in a quotient like that for the derivative. Okay? How are we going to do that? Well, remember, we know that x is equal to r times the cosine of theta. So there's an expression for x in terms of theta, essentially. We have to find what r is, but we can put it in terms of theta. And likewise, right, we know that y is r times the sine of theta. So again, we can rewrite y in terms of theta using this relationship right there. All right, so let's take a look at it here. We're going to find a few calculations. We're going to find dr d theta, okay, which is the derivative of r with respect to theta. We're going to find dy d theta, okay, so the derivative of y with respect to theta, and then dx d theta. Well, you get the idea. We're also going to find the slope of the tangent line, which that means, what will that be? So the tangent line, what represents that? We already talked about dr d theta, we talked about dy d theta, we talked about dx d theta. Slope of the tangent line will be described as the dy dx. Okay, slope of the tangent line is the derivative of y with respect to x. Okay, and then to this curve right here, r equals 4 cosine theta at theta equals pi over 4. Okay, and we're going to explain the meaning of each in the context here. Okay, so let's jump right in here. We'll do dr d theta first. And these are kind of in order of ease of calculation, I guess I'll say. So we're going to take that dr d theta, which we know is equal to, well, r is 4 cosine theta, so what would dr d theta be? So yeah, what's the derivative of cosine? It's negative sine, so it'll be negative 4 sine of theta. Okay, we're just going to take the derivative of this thing here with respect to t. Okay. And then we're going to evaluate that at theta equals pi over 4. Okay, so we have negative 4 sine pi over 4. Okay. We know the sine of pi over 4 is root 2 over 2, so we'll have negative 4 root 2 over 2, which is negative 2 root 2. So, what does this tell us then about our curve? R equals 4 cosine theta. dr d theta is negative 2 root 2. A negative derivative normally tells us what kind of behavior? A negative first derivative means what does that tell us about the original function? Decreasing, right? It's decreasing. What is decreasing in this case? R. So, right, R is decreasing. I want to be a little bit careful here because if R is decreasing, if R is positive, we're going to be getting closer to the pole. If R is negative, we're going to continue to go further away from the pole, though, right? Depending on what value R is, right? But in this case, you're right because R will be positive, okay? So, yes, this means the radius is decreasing at theta equals pi over 4. Okay. And I'll say or, in parentheses here, or getting closer to the pole since, let's see here, R equals, and then let's see here, it'll be 2 positive 2 root 2 when theta equals pi over 4. Okay, so radius is decreasing at theta equals pi over 4. That is true no matter what your R value is. But then we can say even more specifically here, this means that our curve is, we're getting closer to the pole. We're moving in towards the pole because our radius started positive and it's changing at a negative rate, so it's decreasing, right? So a positive radius that's decreasing is going to go towards the pole. Okay, especially at the point when theta equals pi over 4. Okay, so exactly right. Very good. All right. This is like those problems we were doing with the parametric equations where we were using like dy dt and dx dt to determine when the curve, when the particle was moving closer to the y-axis or further away from the y-axis or close to the x-axis or further away from the x-axis, right? You had to know where the point was to then determine are we moving closer or further away, in addition to whether it was increasing or decreasing kind of thing. Okay. All right, let's try and find dy d theta. Okay. Well, here's the problem, right? We don't have a relationship that relates y and theta. All we have is r equals 4 cosine theta. But we have that conversion that we use, y is equal to the r times the sine of theta. Okay? But now we have y in terms of both r and theta. We need to have this only in terms of theta, right? Because we want to take the derivative with respect to theta there. But what is r in this scenario? 4 cosine theta. So we're going to replace this r with a 4 cosine theta for this particular scenario, right? Because that's what our r is equal to. R. It's not like a pilot. Okay. So now we have y in terms of only theta, and so now we can take the derivative with respect to theta. And so dy d theta, well, to take this derivative, what do we need to use? Product rule, exactly right. All right, so we're throwing it back to like September of 2017 here. Okay, so we'll do the second times the derivative first. Plus, remember the product rule has plus in it, folks, right? You're adding the second part, okay? Plus the first here times the derivative second. Which if I simplify that a little bit, it's negative 4 sine squared theta plus 4 cosine squared theta. Can we use the Pythagorean identity here? Sine squared plus cosine squared? Yeah, no, because we got a negative sine squared there, right? And even if we factored a negative 1 out, then this would become positive, but then this would become negative. And there's no way you can kind of like correct for that, really. I mean, we could like solve that sine squared plus cosine squared equal to 1. We could like solve it so that like we know that, for example, sine squared is equal to 1 minus cosine squared. So I could replace this sine squared with 1 minus cosine squared and then simplify things if I wanted to. But nah, let's just evaluate here. So we'll evaluate that at theta equals pi over 4. Okay. So that's going to be negative 4. And then sine of pi over 4 is root 2 over 2, but that's going to get squared. And then plus 4 cosine of pi over 4 is also root 2 over 2, and again, that's going to get squared. Okay. Which is then 2/4, but times negative 4 gives us -2. And then again, 2/4, but times 4 gives us a +2, and so we equal 0. So a derivative equal to 0 means what? Horizontal tangent line in this case. Yeah, we have a horizontal tangent. To our curve. And we can also say y values, right, because this is the derivative of y, the change in y with respect to theta, right, the y values are not changing at theta equals pi/4. The change in y over the change in theta, right, the change in y with respect to theta is 0. So we would expect there to be no change in our y values here. And we'll see that actually in a second. We'll actually be able to show that. Okay. All right, let's try dx d theta. And how about you guys go ahead and give this one a try? Okay, I'll help you get started here. We're going to start the same way that we did before. Y is equal to r sine theta. So in this case, we're going to use x, right, which is equal to r times the cosine of theta. But what is r in our scenario here? 4 cosine theta. So you're going to substitute that in, and then you'll have everything in terms of theta, so you can take the derivative. If you want to simplify your original, x in terms of theta, you feel free to do that. Make it, cosine squared. But go ahead and take the derivative there, see what you come up with. And then try to think about how you would explain the meaning of that value that you find when you evaluate a pi/4. While you guys are working on that, I'm going to pass back some more papers here. I have both problem set 11 and 12 to pass back. I've had problem set 11, I just never returned it to you. But Anyone want to volunteer an answer? No, yes. All right, you should have gotten -4. Okay, -4 is your answer there. Again, is it so important that you get this? It depends on the context of the situation, right? You could kind of stop right here if you wanted to. You could have stopped with cosine of pi over 4, sine of pi over 4 there and circled your answer. Again, depending on the context. We want to be able to explain the meaning, though, which we want to look at the sign, right? The SIGN, whether it's positive or negative. So at this point, right, it's easy to determine what the sign SIGN will be. You don't necessarily need to find that. Up to you. What does this -4 dx d theta mean, though, in the context? -4 means our original function is what? A negative first derivative means what about our original function? It's decreasing, right? Decreasing. So what is our original function here? Well, it's x in terms of theta. So it's just like our, kind of like left and right movement you can think of, right? Just like here, we could say our y values describing, our up and down movement. Okay, it's not changing. So here we could describe this as being there's no left or right movement at, there is a movement left. So we're moving to the left. At theta equals pi over 4. Okay. Oops, off the screen. There we go. Okay, moving to the left at theta equals pi over 4. Which, again, we're kind of like mixing our, r's and thetas with our x's and y's here, right? We're writing x in terms of, theta, and so that allows us to talk about moving left and right when we're talking strictly polar, right? We don't really talk about moving left and right in polar equations with just the r's and thetas, but we bring in the x's where we can now talk about moving left to right, up and down with the y's, stuff like that. Okay, and then finally, the slope of the tangent line, our last calculation we want to do here. Okay, which again, the slope of the tangent line is dy over dx, which we know is equal to dy d theta over dx d theta. Okay, which thank goodness we've already calculated those, right? dy over dx is going to just equal our dy d theta. I'm going to use my simplified version of it right here. So the -4 sine squared theta plus 4 cosine squared theta. All over, and I'm going to use my simplified version right here, -8 cosine sine. And we're being asked to evaluate that at pi over 4 as well, at theta equals pi over 4. Okay. But right, we already know what these values are, don't we? It's going to be, right, we evaluated the numerator already at pi over 4, we got 0. We evaluated the denominator already at pi over 4, we got -4. So 0 over -4 is 0. Is 0. So again, that's expressing that kind of horizontal tangent line and stuff like that. Okay? So just like in parametric, right, we could identify horizontal tangent lines. They occur when dy d theta in this case is equal to 0, but simultaneously to that dx d theta cannot equal 0, right? And then vertical tangents, we'll take our denominator, which is going to be dx d theta, and that's got to equal 0. But again, we don't want simultaneously to that dy d theta, we want that to not equal 0, right? They can't both be 0 because then it's indeterminate. Okay? Now, I left this little polar graph in here for us to kind of get an idea about what 4 cosine theta actually looks like so we can actually compare our calculations here to what we see in the graph. All right, so I'm going to do a quick little sketch. Oh, there we go. Okay, theta equals 4, or sorry, theta and then r equals 4 cosine theta. Okay, so again, I'm just going to pick pi over 3s in this case because again, cosine of pi over 3 easy to calculate. It's 1/2, right? And then I'll use pi over 2. I'll use 2 pi over 3, and I think we actually will be fine if we just go up to pi here. Okay, let me rewrite this. r equals 4 cosine theta. Okay. All right, so here again, we'll plug in our 0. Cosine of 0 is 1 times 4 is 4. Pi over 3 cosine pi over 3 is 1/2 times 4 is 2. Pi over 2 cosine of pi over 2 is 0 times 4 will still be 0. 2 pi over 3. Cosine 2 pi over 3, now it's negative 1/2 times 2, so it'll be negative 2. And then cosine pi is negative 1 times 4 is negative 4. Okay? So at the angle of 0, we're going to go 4 towards the 0, right? So here's 0, our polar axis. We'll go 4 towards the 0. And so there's our first point. And then at pi over 3, angle pi over 3, we're going to go 2. So remember, pi over 3 is this guy right here, right? So out 1, 2. So there's that point. Okay. And again, to connect these, all right, this is where we want to be, kind of watching ourselves, right? This is a continuous function. So as we turn, as we rotate from that 0 to this pi over 3 angle, we have to decrease our radius from a radius of 4 to a radius of 2. So that means we're going to be moving in closer to the pole as we rotate counterclockwise here from our angle of 0 to our angle of pi over 3. So we're going to look something like this. Okay, like that. We're going to rotate in. All right. Then we'll do pi over 2. And at pi over 2, we are at 0. So here's pi over 2, and we're 0. So we're going to continue rotating from pi over 3, right? We have this much to rotate through. But as we rotate through that, we're going to have to rotate right down to 0. Like that. And rotate right down to 0. And decrease down to 0 there. And then at 2 pi over 3, which is in this direction, right? 2 pi over 3, we have to go from 0 to negative 2. So that means we're going to go through all these negative radii. So instead of going towards the 2 pi over 3, we're now going to go away from the 2 pi over 3 and out 2. So to there. And again, all these negative radii from here to here, end up going then from here to here, like this. Like so. And then pi is negative 4. So at pi, we're going to go back forward to here and actually end up rotating right around to there. Okay. Now, believe it or not, this is a circle. All right, it is a circle. If you graph it on your graphing calculators there that are handy, you'll see. But let's see some of this behavior that we were talking about earlier, right? So for example, we know that at pi over 4, we're supposed to have dy d theta. We're supposed to have a horizontal tangent line at pi over 4. Well, if you look here, here's the angle pi over 4. Here's the angle pi over 4. And wouldn't you know it, right there on our curve, it looks like we do have a horizontal tangent line right there. Right? There's pi over 4. And a horizontal tangent. Okay? Also, what's supposed to happen at pi over 4? dx d theta is supposed to be negative. Well, as we rotate around here, are we not moving to the left?
Oh, we are.
We are. Exactly. Yeah. All right. What about dr d theta? Dr d theta at pi over 4 is supposed to be negative. That means our radius is supposed to be decreasing. As we kind of move along here, are we moving in closer and closer to the pole?
We are.
Yeah, we are. We are, right? Okay, so there it is. There's the idea. Okay, we're kind of moving around this way, all right? That's how we rotated it with our theta increasing. Okay. Now, normally I don't put arrows there, but I'm putting the arrows to just show that motion, right? So we are moving both left and we're moving in towards the pole there. So all those different things you can kind of account for in the diagram. Right? Any questions on any of that? All right, let's move on here then. So, next question here, example 5. We're just supposed to find all points, r comma theta, of horizontal and vertical tangency to r equals 2 times the quantity 1 minus cosine theta, only for theta values between 0 and 2 pi. Okay. So, if we want horizontal tangent lines, what does that translate to?
dy over dt equals 0.
And well, in our case, dy d theta. Yep.
My bad.
Equals 0. That's okay. And I guess really, I mean, the t's and thetas technically would be interchangeable, so I think you're okay with saying that, as long as you understand that. And then for vertical tangents, what would it be? dx d theta, right? We want that to be equal to 0. I guess I should say comma here, dx d theta not equal to 0. And then here, comma dy d theta not equal to 0. Right? And we never want them both to be 0 at the same time. It's indeterminate there, and that means we wouldn't have, really either 0 or undefined. Okay? So, Let's take a look at this. So for our, let's do horizontal first. Okay, for our horizontal, we need to find what dy d theta is. We want to set that equal to 0, right? But in order to find dy d theta, we first need to know what y is, right? We don't have anything talking about y here, but we know that y is equal to r times what? Sine theta. And what is r in this scenario?
2 times 1 minus cosine theta.
That's exactly right. 2 times 1 minus cosine theta. So we'll just substitute in for r here. And I'm going to go ahead and distribute that 2 and make it 2 minus 2 cosine theta. And then times the sine theta. I think I'll just make it a little bit easier for ourselves. Okay. And now that we have y in terms of theta, what can we do? Or what should we do now? Take the derivative. Okay, so we'll do dy d theta, and it's a product rule, exactly right. So second sine theta times the derivative of the first. So the derivative of 2 will be 0, but then minus 2 times cosine theta. Derivative of cosine is negative sine, so you get positive 2 sine theta there. Okay, plus, and then the first times the second derivative of sine is just cosine. Okay, which if I simplify that, make it look a bit nicer. 2 sine squared theta plus 2 cosine theta minus 2 cosine squared theta. And we want to know when this is equal to what? 0. Okay, we'll set it equal to 0 there. Now, we're actually going to use this, we're going to solve this using our calculators here. Okay, you can do this one by hand. It's not terrible. You use Pythagorean identities here, but we're going to use our calculators. Okay? And the reason why I want to do that here is to show you, you don't need to be in polar mode in order to solve this equation, right? Yes, we're talking in a context of polar, kind of a situation here, but this is just x. And you want to know when this function here is equal to 0. That's it. So you don't need to be in polar graphs. In fact, I would suggest not using polar graphs here. So we'll just go to the mode here. We'll change back to function. Well, if I don't miss it, there we go. Okay. And then to solve this, I'm just going to put 0 if you want here. Actually, you don't even need to graph the 0 here. I'm not going to do that. So we'll do 2 sine of x squared plus 2 cosine of x minus 2 cosine of x squared. Okay. The reason why I switched us from polar to function, well, part of the reason is if you try to graph this, when you go to second trace, there is no like 0 command when you have polar graphs. You can only find the derivative with respect to x, or dy dx, or you find the dr d theta, right? It doesn't have like a zeros or something like that, and so that's why it's not really helpful to graph it in polar equation or polar format. But if we go back to function, right, and we graph this thing, we want to know when it's equal to 0. We can do second trace, and now we can use the 0 command there. Okay, it makes it a lot easier. All right, which, let me see here. If I make it, oh, that's another thing. I'm going to adjust my window here, too, because we only want to be for theta values between 0 and 2 pi. So I'm going to, instead of going from -5 to 5, I'll go from 0 to 2 pi there. Excuse me. Like so. All right, so then we go to our graphing calculator, graph it. Okay, voila. And so we have what looks like a 0. Let's see here. So it looks like we have a 0 at 0. I'm going to go over there and just check that out to make sure it's right. I think it'll let me go to the left of 0. Yes, it does. Okay. So I'll go to the left of 0 here, right? Go to the right of 0, and then guess just to make sure. Yes. Okay. And so that's I have calculator rounding error there, but that is going to be, we'll call that 0. Because again, what is that? That's -4.55, and that e -7 is times 10 to the -7. So it's like 0.000000000, or negative 0.000045556. It's 0. Okay, so it's at 0, 0. So at theta equals 0, which is like our x here. So at theta equals 0, we have a solution. Okay. Now let's find another one here. Find another 0. I see this one right here. It's so fun. Just holding the arrow key. There we go. Right of it, and then guess. And then we get this decimal here, 2.0943951. Okay, so we'll write that down here. I'm going to write down the whole thing. 2.0943951. Okay, and then we'll go to 0 for the other one over here. Left and right, 0, and we get 4.1887902. Okay, like that. Comma, and then I'll do the very last one here and make sure I have my window at 0 to 2 pi. So that way I can see. I think it does. Let me do it this way. All right.
Just hold while it graphs here.
So we had a 0 here, 0 here, 0 here, and let's see. It looks like we have a 0 there at 2 pi. We do have a 0 at 2 pi, but do we want to include 2 pi as a solution? Nay. Okay, because we have not including 2 pi there. So those are our 3 solutions right there. Okay, now, we know that sometimes, right, pi shows up in our thetas, right, because we're talking about radian angles here, and so sometimes we wonder, like, maybe, is this a nice radian measure here? And so I think, let me type in. Okay, so what you can do to kind of like try and figure out if this is a nice radian measure or if it's just some random decimal is take that decimal, all right, so in this case 2.0943951, and I'm going to divide a pi out of it, right, because normally our radian measures have pi in it, so if I divide a pi out, hopefully that'll show me what the decimal is, and lo and behold, we get something that's pretty close to 2/3, right? And in fact, if we type 2 pi over 3 into our calculator, you'll see there's the 2.0943951 that we had before. And so this is 2 pi over 3. Okay, likewise with the 4.1887902, if we divide that by pi, it's 1.3333, which, you know, as a fraction is 4/3. Okay, or in other words, double the 2 pi over 3. Okay. No, like I said, this one, it does not require a calculator. What you can do is you can replace sine squared with 1 minus cosine squared, and that gets everything in terms of cosine. You'll have like a quadratic. That's all cosines, though. Like instead of x's, it's cosines, and then you can factor the quadratic and set each factor equal to 0 and solve that way. Okay. It's not, well, I mean, and I'll just real quick here. 1 minus cosine squared theta. Okay, so again, I just replace the sine squared with 1 minus cosine squared. I'll distribute the 2. Okay, so we'll have, and this is still equal to 0. I'll distribute the 2 here, so we'll have negative 2 cosine squared, but that's another negative 2 cosine squared there, so we'll have negative 4 cosine squared theta, and then 2 times 1, 2, right? So we'll have a plus 2, plus 2 cosine theta. Well, it's negative 2 cosine squared because of that, and then negative 2 cosine squared because of that. They'll be add up to make a negative 4 cosine squared.
Oh, yeah.
And then 2 cosine, and then plus 2 there. Okay? And that's equal to 0. And then if you multiply both sides by negative 1, that makes it a positive 4, a negative 2, and a negative 2 like that. And then this does factor to 2 cosine theta minus 2 and 2 cosine theta plus 1. Whoops, I should have included the parentheses there. Okay, it's like that. So it does factor, and you said each factor equal to 0, and you'll then get these solutions based off of that. Okay? So there's that. Okay, so whew, that was fun. So there are our thetas, right? But we have we want to find the points, r comma theta. So we have our thetas, right? We have 2 pi over 3. We have the 4 pi over 3. And we also have the 0. Right, we've got to find these missing r values. And how can we find these r values given that we have the thetas here? What can we use? Yeah, so you can plug it in for r way back up here where y is equal to r times the sine of theta. Okay, we're going to use that, or sorry, not into r, my bad. We're going to use the original equation right up here, my bad. This one right here. The r equals 2 times 1 minus cosine theta. 2, can't write, 2, 1 minus cosine theta. Okay, and this equation, right, of course, relates the thetas and the r's and stuff like that. Thanks. Okay, appreciate it.
Hi, Mr. Goff.
Hello, nerds.
Did he? No, but I told him about it, though. I don't know if he went and watched it or not. We'll see. Anyway, so right, we can plug these in, right? So 0, cosine of 0 is 1, minus 1 is 0, so we get 0, 0. 2 pi over 3, cosine 2 pi over 3 is negative 1/2. 1 minus negative 1/2 is 3/2 times 2 is 3. And then 4 pi over 3, cosine 4 pi over 3 is also negative 1/2. 1 minus negative 1/2 is positive 3/2 times 2 is 3. And so there are our locations. Okay. All right. Now we're going to do vertical. Hooray! All right, I'm going to let you guys try this one here, so I'll help you get started. Vertical.
Wait, can I see the bottom of that?
Yep,
really quick?
yep.
Sorry. Okay, thank you.
You're good. All right, so for the vertical ones, again, we want to find now when dx d theta is equal to 0. But in order to find dx d theta, we have to find everything in terms, or x in terms of theta. So we have x equals r cosine theta, right? But now x is really the 2 minus 2 cosine theta times cosine theta, which is then really nice. It's just 2 cosine theta minus 2 cosine squared theta. It goes together much nicer than the dy d theta did, or dx, or sorry, the y did. It goes better together than the y did. Okay, so I'll let you guys go from there. Find dx d theta, right? You want to know when it equals 0, and figure that out. This one you shouldn't have to use a calculator for, even like, well, we didn't need one for the other one either, but in this one, again, you can solve this one without a calculator. Okay, so give that a try. Say again? I'd like you to, yeah, I think it will help, yeah. Don't forget to use the chain rule when you take the derivative of 2 cosine squared. Remember, don't forget to find the actual points, right? Not just the theta values that give you it. You have to find the points r comma theta. Make sure you answer the questions being asked there. graphing it. Do as I say, not as I do. I know, right? So proud.
Well, I'm so proud. I can't wait for the homework.
It's supposed to be like 4 problems.
Six will be shorter than this. Example 6 is shorter than this one. Yeah.
That way it explains so much.
Yeah, look at the space. Example 5, much longer. Example 6, it's like example 5 is like 2/3 of the page. Example 6 is like
It doesn't work
1/3.
like that, especially on your quizzes and tests. You think that, except like it never happens.
You still have to find dy theta and dx theta. You just don't have to solve for zero.
True.
I give up. I can't find the derivatives of.
Should be negative 2 sine theta plus 4 cosine theta sine theta is what it should be. Yeah.
What?
Oh, question on that. I'll just show it. All right.
Well, now I feel like a cheater.
Well, you're looking.
Oh, I forgot the line.
You should have.
I did. Never mind, I did.
So if you take the derivative of
Oh, she was bad. So
right, so you're taking the derivative of this, the output function is the square.
why
So like this is the derivative of something squared, so 2 in front,
should be
times and then you leave what's inside, and you multiply by the derivative of what's inside.
Yeah, watch him pull a Mario and make us get a 17 out of 20.
Yeah, but you understand that when you turn it over on the
So
other
it's up
side.
here. And you get this. 2 goes out front, times -2.
Yes.
So it's -4. Leave the cosine, times the derivative of the cosine, negative sign. That's why it's negative becomes positive. Does that help? All right, so anywho, there are answers. Now, there's an overlap here, isn't there?
No.
Theta equals what?
0.
0. What does that mean? That means at 0, dy d theta and dx d theta are both 0. It's indeterminate. We have to exclude it. Throw it out.
Oh, come on.
Where are we going?
We're going
Come on.
downtown.
Come on. Downtown?
Yeah.
Nice. That's where all the lights are. There's a song. I don't even know if that's the right lyric for the song, but you guys ever heard that? Downtown? No? Okay, never mind. So we can't have both dx dt, or sorry, dx d theta, dy d theta, I'm throwing in the t's now, equal to 0, right? Because then we have the dy, we'd have dy dx indeterminate. All right, so we throw out the 0, not because they're both zeros, but because they're both the same number, right? If we had a 2 pi over 3 here and a 2 pi over 3 here, we'd throw those out too, right? If we had a pi over 3 and a pi over 3 here, we'd throw those both out too. Okay. If you look at the graph of this thing, we can actually see these horizontal and vertical tangencies that we just identified. All right, so if you'll permit me here to show that. Well, I don't know. This is I prefer to. This is maybe a psychological experiment. You kind of see what you want to see, I guess. So. I guess right. I guess we understand. Okay. So anyway, we know that now.
Okay.
So if there was a question before, there's not one now. All right. So, all right. We'll go to second calc, and we'll go to value here to kind of identify some points. Looking for theta. So I'll put in like I don't know, 2 pi over 3. It will be, yeah. Someone can like remix this. Someone could remix it with like Sir Mix-a-Lots, I like big butts after that, kind of thing if they wanted to, So that could be fun. Anyway, you can see there's our point, right? There's our point, and that's a horizontal tangent. That's a horizontal tangent right there, right? There it is. It located it. Second trace value, I'll go to 4 pi over 3. Okay, 4 pi over 3, we're down here. Again, you can see that horizontal tangent. Okay, let's go to pi. At pi, we're right here. Okay, you can see vertical tangent. All right, let's go to pi over 3. Horizontal or vertical tangent. And let's go to, wait a minute, did I mess up? 5 pi over 3 is what that's supposed to be. And then value, let's go to 5 pi over 3, and we'll see another vertical tangent. Let's go to 0. 0 is right here, right? And that's where we have that indeterminate form. Well, again, if I kind of move away there from it, what do we know, right? That's a pointy part of our graph, right? We've seen that in the past, like, right, many moons ago, right? But the idea is when we have those pointy parts in our graphs, right, the derivative doesn't exist. dx doesn't exist, right? In this case, because, we have a sudden change in the slopes there like that. Right? So anyway. All right, last piece here, last piece. We're going to find the equation of the tangent line to r equals sine theta at theta equals pi over 3. To find the equation of a tangent line, what two things do we need?
d theta.
So slope, a tangent slope is not dy over d theta, dy dx. We want dy dx, which then will use dy d theta over dx d theta.
We do need dy over d theta.
In the long run, we do, yes. So, good job. Okay? And we also need a point. All right, to find dy dx, we need to know dy d theta and dx d theta, which means we have to go back to, y equals r sine theta, right? That little function that we know, the relationship that we know. We'll plug sine of theta in for our r. So y is really equal to just sine squared of theta. Okay, and therefore dy d theta will be 2 sine theta cosine theta. Okay, so let's see here. I'm going to run out of space if I do it there. So, well, maybe not. Maybe so. Oh well, we'll try it. Okay, and I'll do the same thing for x, right? X is equal to r cosine theta, but r is sine of theta, so x is really equal to sine theta cosine theta, which we get to use our product rule. Hooray! Dx d theta. So second times the first, derivative of sine is cosine, plus the first, sine theta, times derivative of second, so it's going to be negative sine theta right there. Okay, so dx d theta is cosine squared minus sine squared. And we're going to evaluate that at theta equals pi over 3. Okay, so we'll have 2 times, sine of pi over 3, root 3 over 2, times cosine of pi over 3, 1/2, over, cosine of pi over 3, 1/2, but squared will be 1/4. Sine of pi over 3, root 3 over 2, but squared will be minus 3/4. And so we'll end up with, well, that's going to cancel with that. We'll end up with root 3 over 2 in the numerator over negative 2/4, right? 1/4 minus 3/4, 2/4 in the denominator, which simplifies to negative root 3. So there's our slope, negative root 3. There's our dy dx evaluated pi over 3. And we need to come up with a point. We have one, we have the theta is equal to pi over 3. But for our point, right, it's an equation for a tangent line. We need to come up with the x and y coordinates here. We need an x and a y for this. Plug it in, okay? So to find our x coordinate, we're going to go back to x equals r cosine theta. Okay? What's theta? Pi over 3. Ooh, what's r though? Right, r is sine of theta. So all we have to really do here, we can, find sine of theta, or we could use this version here where we have x in terms of, we can just say this is equal to really then just sine theta cosine theta here. And then we can just evaluate that at pi over 3. Okay, is sine pi over 3 cosine pi over 3. And again, if it's a free response question, you don't need to evaluate these. You can just like use that. That's my x value if you wanted to, but you know we're here, so let's just go ahead and take care of this. So sine of pi over 3 is root 3 over 2, right? Cosine pi over 3 is 1/2, and so we get root 3 over 4 for our x value there. And we'll do the same thing for y. Y is equal to, I'll just go ahead and just use the sine squared of theta there that we know. Okay, and again, evaluate that at theta equals pi over 3. So sine of pi over 3 is root 3 over 2, but square will be 3/4. So our answer is y minus 3/4 equal to negative root 3 x minus root 3 over 4. Nailed it. Okay, got it there. With plenty of time left. Alrighty. Questions on any of that? Okay. So understanding these relationships, right, is key, right? Understanding, you know, if I'm asking for what I'm asking for, right? Equation of a tangent line, dy dx you need for the slope, right? A point, x, y, for the, you know, coordinates x and y and stuff like that, for your point, you know, kind of thing. So, and of course, dy dx, knowing that that is dy d theta over dx d theta, super important. So, alrighty. Any questions for me about that polar stuff?
I was thinking about getting back on, but I got done around I wanted to take a break at like 9:30, and then I was like, nah, it's not a good idea. I'm gonna go.